Welcome back. In this video, we will look at exploratory data analysis, something we will refer to as EDA for the rest of this course. EDA is unstructured exploration. There is not a set of sequential activities that you must perform. So there is no checklist that I can give you that you need to use for performing EDA. Generally, you probe the data, and depending upon what you discover, you ask more questions or you ask different questions. Normally, tabular data is the most common data type that you will encounter, even though unstructured data is increasingly becoming more common. And tabular data is the kind of data that we have seen in the previous video through data frames. This is data that is laid out as tables, which is two-dimensional structures. There are rows and then there are columns. The columns are defined and understood, and we generally understand what they contain. Unstructured data, however, is generally a reference to text data or audio or other perceptual types of some type, as perceptual data of some type. But even that will almost invariably need to be converted into structured arrays with defined dimensions. But for the moment, we will skip all of that. There are specialized techniques to deal with unstructured data. What we will also not cover for the moment is the exploration of time series data. That will be covered in the video on time series. So coming back to tabular data, data is laid out as a two-dimensional matrix, whether in a spreadsheet or in a Python data frame or maybe in a database table. And generally, rows represent individual observations, whereas the columns, the vertical columns, they are the fields or the variables. The variables themselves, they can be numeric, so they can be numbers, or they could be categorical variables. In that situation, you will see strings instead of numbers in the columns. Now, numerical variables, they can be integers, which means they're whole numbers, or they could be floats, which is another way of saying that these are numbers that contain decimal digits as well. And numerical variables, they tend to be continuous, which means in a range, they can take any value. Categorical variables, they may be cardinal, for example, species, gender, names of countries, which means there is no order to them, or they may be ordinal, so things such as low, medium, high, economy, business class, first class, and so on. And they generally belong to a discrete set. Sometimes categorical variables may also be referred to as factors or levels. As we progress into the course and get to machine learning, we will find that algorithms often require categorical variables to be converted into some sort of numerical representations or numerical variables or arrays. And there are techniques to do that, something we will cover later in the course. Now, for analyzing tabular data, we will be using pandas a lot. And pandas offers several different functions for reading different types of data. So you can read data from SAS data sets, from databases using SQL. You can read JSON data, you can read web scrape data, you name it. There is generally a solution for every kind of data that you might run into, that you might need to read with pandas. When you're performing EDA, you normally want to explore data in an unstructured way and try to get a feel for the data. And the kinds of questions that you want to answer are: how much data do we have, which is generally the number of rows in the data, and how many columns do we have, so how many fields appear in the data set. What kind of data types are there in our data? So which of the columns are numeric, which of them are categorical variables, which are dates, which are just strings or texts. What are the names of the columns, and do the names of the columns tell us anything? Is there a data dictionary we can get our hands on? Sometimes we may just want to review a sample of the data set. Just show me a few of the observations because I want to get a feel of what the data actually looks like. Sometimes we may also want to examine, is the data set complete? Are there missing values in our data? And if so, then how many? For columns that are categorical, we may want to see what are the unique values. So for example, if we are looking at the names of countries, we may want to see how many unique country names are there. Sometimes we may also want to see how many observations exist for every country. So which means we want to divide the observations by every category to see, uh, is our data spread out equally across the categories or not. For numeric columns, we may want to see the minimum or the maximum values. We may want to see what the average is. We may want to see what the spread is using standard deviation or variance. We may actually want to see a histogram for some of the columns, just to get again a feel for the data. And very often we would also want to look at correlations between the different columns, because maybe the correlations between some of our data fields is so large that they are almost proxies for each other. So we may want to see that. So these are the kinds of things we will explore doing as part of uh, exploratory data analysis. And we will start with the diamonds data set. The diamonds data set has about 53,000 records, each representing a single diamond. Uh, each observation has the weight of the diamond, the price, and various other attributes relating to the diamond. And we are going to perform some exploratory data analysis on that. With that, I'm going to start screen share, and you can use the same notebook. You can download it from the course website. And this is the same notebook that we used in the previous video as well. And now we are at the section on uh, reading data with pandas and EDA on the diamonds data set. So we will run these cells. What we have here is the data dictionary. This describes what the columns of our diamonds data set are. First, we will load the data from Seaborn, which is where this data is. And as we load it, we also print the data frame just to see what it looks like. So there are 53,940 rows. There are 10 columns. And these are the descriptions for each of the 10 columns. When we just print the data frame and all the rows cannot be printed together, Python is going to print out just the first 5 rows and the bottom 5 rows and put the dot dot dots, the ellipses in the middle. So that shows us there are other rows in the middle. Pandas has a very useful describe function. It provides a variety of summary statistics. So for example, since we have put our data in a data frame called df, all we need to do is to write df.describe, and it gives us some basic statistics on all of our columns. So here we get to see how many values exist in the caret column, in the depth column, table, and so on. And these are all identical. And what that tells me is that there are no missing values. It gives me the mean. So the average caret age in our 53,000 diamond data set is 0.79. The average price is 39.32, and so on. It also gives me for every column the standard deviation, the minimum, the maximum, the median, which is the 50th percentile, the 25th percentile, and the 75th percentile. However, notice that we also had some columns that were categorical. So we had the cut column, which had entries such as ideal, premium, good, and so on. Similarly, we had the color column, which had E, I, J, D, and such entries. And the clarity had things like SI2, VS1, and so on. And we don't see that here in the results of the described function. And the reason for that is you can't produce a numerical summary out of this. However, you can use the describe function on just this subset of the data, which means you take the df and select only the columns that are categorical, and you run the describe command. And this time you get a slightly different output. Pandas realizes that these are categorical variables, and it lists you the count. It also tells you how many unique values it finds in each column. It also says which is the most frequently appearing value, with a count of how many of those appear in the data. So it tells me that there are 21,000 diamonds with the cut equal to ideal, and there are 5 such categories. If I wanted to see this and this together, all I have to do is to include the parameter include equal to all in my uh, command, and it gives me everything together. And this time cut, color, and clarity are included as well. But notice that there are a lot of nan values or blanks or nulls that are introduced in here because pandas has had to marry and join these two tables together in a way that would make sense, and this is the only way to make sense. So for the cut clarity and color columns, all the mean, standard deviation, minimum, maximum, all of these are blanks or nulls, and the unique, top, and frequency here don't make sense for the numerical variables, and these appear as nans. Notice that by default, the describe function had the 25th, 50th, and 75th percentile. You can change it. For example, I can change it by specifying the percentiles I would like to see. So I want to see all the percentiles from 0 to 1 with a step size of 0.1. And when I do that, I get a much larger table. So I get all the percentiles 10, 20th, 30th, 40th, 50th, and so on. And I can see the distribution of my data. Another useful command is df info. So I can put info after my data frame name, and it gives me information on what kind of data type is contained in each of the columns and how many non-null entries are there. So here I don't have any missing values because I can see that there are 53,940 non-null values in all of the columns. So I'm pretty good from a missing values perspective on this data set. I want to see how many rows and columns I have in my data frame, and I can do that by asking for the shape of the data frame, and it gives me a what is a tuple, and it tells me this is the number of rows and this is the number of columns. So I have 53,940 rows and 10 columns. If I want to see the names of my columns, I just type in df.columns and it gives me the names of the columns here: caret, cut, clarity, and so on. I can explore individual columns and I can calculate measures of central tendency, variability, association, etc. So all of the descriptive statistics that we covered in one of the prior videos, we get to see how these are actually calculated using pandas. These are the function names that you can use, and let us see all of these in action next. So if we have to do uh, the mean, for example, if you want to see the mean for our diamonds data set, I can just ask it to calculate the mean for the data frame. And notice that I have to write numeric only is equal to true. Otherwise, I'll get an error as it tries to calculate the mean of the cut clarity and color, and that cannot, of course, be calculated. So by asking for the mean of the entire data frame and only the numeric columns, it gives me in every line the mean for each of the different columns that are numeric. So it's pretty self-explanatory. However, I may be interested in finding out mean of, say, just one of the columns. And I can easily do that by limiting my selection from the data frame to that particular column name and get to see the mean this way. And this, again, this 0.7979 is the same as the 0.7979 that I see here. Similarly, I can calculate the median. I can calculate the median for just the caret variable as we tried to do for the mean. Similarly, we can calculate the mode and we get the modal value this way. We can also calculate the minimum. We can also calculate the variance. And notice that the response here is in scientific notation. And what that means is that this is this number multiplied by 10 to the power whatever the number here is. So that's what the variance is. I can also calculate the standard deviation, which is the square root of the variance this way. Sometimes you want to look at the data visually, and while visualization is a separate lecture, a separate lab exercise as well, where we will look at visualization in detail, pandas allows us to do very quick visualizations very quickly with just one command. So if I want to see, for example, a histogram for a particular column, I can just type in name of the column and type in .hist, and pandas using the defaults will create a histogram. So this is my histogram uh, of the caratage in my diamonds dataset. So I can see that most of the diamonds are relatively low caratage, and then there are a few that are higher in weight. In the same way, I can do a histogram uh, for the depth, for the cut. Now notice that cut is a categorical variable, and pandas can automatically knows that it needs to create a bar plot of this type where it creates a separate bar, and the frequency, the height of the bar is determined by the frequency of occurrence of that particular categorical variable. And I can see this is what the distribution looks like. Ideal is the most occurring category in my database, in my data, and fair is the least occurring. I can see that here. Uh, the bars have a gap in between them, and that's what distinguishes a bar plot from a histogram. In a histogram, the ranges, because they are continuous, they touch each other. And I can also, by asking for a histogram for the entire data frame without actually specifying a particular column, then pandas is going to do a histogram for all of the numerical columns that it finds in the data. So we can see all of these together. Now, this is really powerful because it allows us to explore the data, ask additional questions, and see what is going on. Uh, when we get to the visualization lecture, we will see that you can control the colors, you can see control the bin sizes and many other aspects of these graphs. But for the moment, this is a high level analysis that you can do very quickly without having to do a lot of work. You can calculate the range by subtracting the minimum from the maximum. And here we have calculated the range for the depth column. In the same way, we can also calculate covariances. And these are the covariances, and this is the covariance matrix, which you can see. And the middle column is the diagonal value here. This is the variance of that particular variable. So caret's variance is 0.22 and so on. We can also calculate the correlation matrix, which is really just the covariance matrix normalized by the standard deviations of the two variables. And here again, you have to pass in the parameter numeric equal to true. Otherwise, it tries to calculate correlations for the categorical variables and errors out. So you need to do that. And you can see that the correlations, uh, the diagonal entry is 1, but you can see the correlations for all of the others. This is a symmetrical matrix, which means that when you look at this is the same as the number here, and so on. We can also calculate the correlation between individual variables. So we just want the correlation between caret and depth, and we just give the correlation function, and we get just a subset of this data here, uh, which is which has only 2 rows and 2 columns. When you see correlations like this, that's a lot of numbers, and it's difficult for humans to understand or comprehend what it actually means. And sometimes a visual may be very powerful. So we can, just by using the heat map command and passing to it our correlation matrix, which is just this, uh, we can get a very nice looking heat map, which looks like this. So as you can see, all of this work can be done with very few commands. Most of this functionality is already built in. There is another parameter that you will see here which says annotations equal to true. And what that means is that I want to see the numbers here, not just the colors. If I take this out, then I will not see the numbers. So I'll see my heat map like this, and this I find to be less useful. So I'm going to change this back to true because I want to see the numbers as well. And here's the scale that is been used for the correlations. All right. Now, you can also calculate the phi k correlations as well. This is something we covered in the higher level video. And this allows you to calculate correlations between all kinds of variables, whether they are categorical or numeric. The only downside is that the calculation is results in a number which is between 0 and 1. So you can't find out the direction of the correlation, but it gives you a good sense of whether there is association between the different variables. So here is the phi k correlation matrix, and cut, color, and clarity are also included. So you can see that here, and you can create a heat map of that. So what I did was, when I calculated the phi k correlation, I put it in a variable called x, and I am able to pass x to my heat map function. And again, I put annotation equal to true, and that gives me this nice looking heat map, and it allows me to spot the variables that are more connected with each other than others. You can also get a detailed phi k correlation report using this function. And again, I will leave it to you to try this out yourself. Another common thing we often have to do is to analyze distributions using quantiles. So we want to see what is the 30th quantile, what is the 50th quantile. So of course, we can get it using the describe functions that we saw before and passing to it the quantiles that we want to see. But if we just want to calculate the quantiles, we can do that like so. So we can ask for uh, the quantile number. So this will be a number between 0 and 1, and it gives me the quantiles for all of the numeric columns in my data set. Sometimes you may want to calculate multiple quantiles. So I want to calculate the 10th, 30th, the 50th, and 75th percentile. And I do it like this, and it gives me the answer in this way. We sometimes have to calculate z-scores. Again, they're very common. We have a function called z-score that we can import from the SciPy library, like so here. And then we can calculate the z-scores. And here are the z-scores for caret and depth. So this is how far they are uh, from zero in terms of standard deviation. Uh, and this is the z-score calculation. Know that when I do this calculation, it returns a data frame, but it does not modify my original data frame in any way. If I want to put these columns in my data frame, uh, I will have to do that separately. And we will see that when we get to data manipulation and transformation in the video uh, later. And then I can calculate the average z-scores, which I expect to be 0, and that is what is confirmed here, because the average z-score for carrots is 2.44 into 10 to the power minus 16, and this one is another number into 10 to the power minus 15, which is roughly equal to 0. I can also look at the standard deviation. I would expect for z-scores, the standard deviation should be 1, because I've already subtracted the mean and divided by the standard deviation, and that's what is confirmed here as well. And there are other functions here. You can sort values, you can count unique values. So many of these we are going to look at in the data preparation video, because these will be useful functions to twist and transform data into a format that we like. Now, data transformation and data exploration are actually quite closely related, and many of the same functions that you would use for exploration are also used for data preparation and the other way around. In fact, data exploration, data visualization, and data preparation, they are all very closely connected. And when you have a full understanding of all of these three topics, you will see how they join together, and they're really just one big topic as opposed to being three different ones. That is an example of sorting the values in our diamonds data frame. And here we are sorting them by first by price and then by table. Then we are also telling it whether to sort the data in ascending order or descending order. And here we pass it two parameters, false and true. So there are two values here in this list here. What that means is price should be sorted not in ascending order, whereas table should be sorted in ascending order, because this is true. And then dot head means just show me the top 5 records. That's all I want to see. And it gives me the first 5 records sorted by price. So the most expensive diamond is 18,823. The next most expensive is 18,818. This all got sorted in descending order because we had set ascending equal to false for the first entry here, sort values, which was price. I can also look at the unique values for cut like so. So I can see that there are 5 different categories that are available in my data set. I can also look at how many are there. And of course, I know it is 5, but if sometimes I'm just looking for the number, I don't want to list all of them because maybe there are 150 of them and I just want to see what the count is. And then N unique stands for number of unique values. That gives me the number of unique values. Value counts is a very useful function. Really just gives you a frequency count for every value in a categorical column. So if I do it for cut, then it gives me that there are 21,551 of ideal, 13,791 of premium, and so on. Another useful function for data exploration is sampling. Every time I type in df, I get the first 5 and the last 5 and dot dot dots in the middle. But I may want to see any random number of rows in my data set. So when I say df sample and I put 4 here, it means that show me any 4 rows from my data frame. And that's what this command will do. And each time I run it, unless I have set the random seed, I am going to get a different set of rows. So it gives me different diamonds each time I run this. So I can keep running this and I find a different set of diamonds coming up each time. Sometimes I may want to change the names of my columns. Again, this kind of falls between the data prep versus data exploration category. And I can do that by just using the rename function. And I say change price to dollars. Notice that what I've passed here is what we saw previously to be a dictionary. So we pass a dictionary to the function, and the dictionary contains a key value pair, and the key is what the original name is, and the value is what the new name should be. This is a very common way of passing parameters to functions. So just wanted to show this. And in place equal to true means don't just show it to me here, but actually make the change in the data frame. If I do this, then I will find that my uh, price function, my price column has changed its name to dollars. So this is this is what I wanted to cover on EDA. So here we saw a large number of things. We looked at some graphing, we looked at some basic statistics, counts, unique values, and such. And next, we are going to cover something very interesting, which is the split, apply, combine mechanism for looking at data. If you are used to pivot tables in Excel, that is exactly what this is. And we will see how to do it in Python and a number of different functions that let us do slightly different things on the split, apply, combine theme. So thank you very much for watching, and I look forward to talking to you about split, apply, combine in the next video.